This paper was given to the American Physical Society Far West Section annual meeting in 2017. In 1957, Bardeen, Cooper and Schrieffer gave us the theory of superconductivity. This links the isotope effect to the lattice distortion which binds Cooper pairs. The isotope effect is weak in HiTc, so we need an alternative link. Fast forward to 1993. The fact that the carriers are positively charged is the most important feature which distinguishes HiTc from low-Tc. This is widely acknowledged, but in fact false, and we need dispersion dynamics to sort it out. What differentiates them? HiTc is the positive Hall coefficient. How come? Charge carriers are holes. What is a hole? An electron vacancy in an otherwise filled valence band. Can the Lorentz force act on voids? No. Or immobile positive ions? No. How can RH be positive? Collapse of start party. Consider first the free particle. If you operate on the stable wave packet with the Klein-Gordon equation, you get a second order equation. This is the same equation as you get if you take Einstein's relativity equation and substitute E using Planck's law and P using the de Broglie relationship. And if you differentiate this, you get an equation with three velocities. The product of the phase velocity with the group velocity is equal to c squared. And if you have to calculate the speed of the electron, you'd better know which velocity you're trying to calculate. I'll plot them in a moment, but first we need the second derivative. The curvature is the inverse of the effective mass. And we can use this inside Newton's law and apply it in the Lorentz law. The effective mass has two terms because mass is not a fixed quantity in relativity physics. Here's the dispersion. Omega is equal to the square root of the rest mass squared plus the k vector squared. And the curvature is positive everywhere. The group velocity is the derivative of the dispersion, is 0 at low k and tends to c at high k. This is exactly as you know it from relativity theory. And beyond the speed of light is the phase velocity. It is singular in the rest frame. Time is Newtonian within the coherence sigma. In dispersion dynamics, the rest mass of the antiparticle is negative and its curvature is also negative. I'm telling you this because the difference in energies between these two states is greater than a megavolt. So the electrons in the high temperature superconductor certainly have positive rest mass. But the crystal fields cause the dispersion to fluctuate. And this results in an effective mass which is sometimes positive and sometimes negative. And we'll consider some examples. The first is copper. This is the metal with the highest conductivity. The valence band is predominantly D-like, with on top of it the S-like band, which is free electron-like and parabolic. K is 0 on the gamma points. Notice particularly that the curvature is positive in the region of the Fermi level, and the Hall coefficient is negative. Consider secondly the semiconductor silicon. The Kronig-Penny model tells you that the semiconductor is a narrow bandgap insulator. The top of the valence band has negative curvature, the bottom of the conduction band has positive curvature. In a p-type semiconductor, the impurity states lie close to the top of the valence band. Electrons are thermalized from the valence band to the impurity states, leaving itinerant electrons in a negatively charged band, curvature, band of negative curvature. The Hall coefficient is positive. Conversely, for an N-type silicon, the Hall coefficient is negative. Consider thirdly aluminum. Weight for weight, this has an even higher conductivity than copper. The valence band is predominantly p-type, with the s-band coming up from below, hybridizing with the valence band and causing a negative curvature in the region of the Fermi level. Calculations show this. The Hall coefficient is positive, the opposite to copper, even though both have electronic charges in their conduction. So we can sum up these few examples. Copper, N-type silicon, and low-temperature superconductors have negative Hall coefficient and positive curvature. Aluminum, P-type silicon, and high-temperature superconductors have a positive Hall coefficient and negative curvature. We need to consider the Hall measurement, the data for HiTc, and the superconducting state. The Hall measurement occurs in two moments. Firstly, there's a transient current, and then a steady state Hall field. If the curvature is positive, the Hall coefficient is negative. If the curvature is negative, the displacement due to the Lorentz force is in the opposite direction, and the Hall coefficient is positive. The same sign as for ionic conductivity. And what about the superconductors? We take it that the most typical and the best studied high-temperature superconductors are the cuprates. And there are three types. YBCO is barium-doped lanthanum cuprate. Barium is divalent, lanthanum is trivalent. This is a p-type superconductor, where p stands for a positive Hall coefficient. YBCO is also doped, but it's doped with anions. The unit cell is large. It has 13 cationic valence charges, and the anion is divalent. So there's a mismatch for stoichiometry. When it's underdoped, the compound is not superconducting. When it's overdoped, the critical temperature is 93 Kelvin. What happens is those oxygen atoms occupy states in the copper chains, and they pull electrons from the copper oxide planes, causing fractional charges in those planes as calculated in Madelung potentials. The fractional charges are signals of holes in the copper oxide planes. The Hall coefficients are positive. BISCO is not doped, but it has some different features. As it comes in several types. The single layer copper oxide plane is like LabCo, and it has a similar TC. And the double layer is like IBCO, and it also has a similar TC. Triple layer BISCO has TC above 110 Kelvin. And the charge distribution, which we calculate with Madelung potentials and see in this chemical model, is typical for holes. And so we can sum up. All carriers are electrons. The p-type superconductors have a positive Hall coefficient and negative curvature. The n-type superconductors have a negative Hall coefficient and positive curvature. Well, these Hall coefficients are measured at normal temperatures. Do the chemical holes disappear at T less than Tc? There's no reason for that. The facts make it obvious that the Coulomb force that binds the compounds in the crystal chemistry binds also the Cooper pairs. However, this gives us a conundrum. The electric field E equals 0 in the superconductor, and the excitonic pairs are uncharged. So what happens in the electrodynamics? How do these materials superconduct? What is the force which causes the conduction? We conclude that the molecular exciton packet reduces at the electrodes, which supply superconducting gap energy, and the electrons are thereby transported without resistance in Newtonian time. Something similar happens in low Tc. And our conclusion is that dispersion dynamics gives a semi-unified theory for low Tc and high Tc.